Lesson 7-7. Our learning target today is I can identify geometric sequences as nonlinear functions. And our essential question says, how do you write an equation for a geometric sequence? So the first vocab word is geometric sequence. A geometric sequence is a sequence with a pattern involving the same number being multiplied over and over or divided over and over. A geometric sequence is nonlinear, and it has a general form f of x equals a times b to the power of x, where x equals 0, 1, 2, 3, and so on will give you the first four numbers in the sequence, and then more with the dot, dot, dot. Now, what's important in this general form is to recognize that a is the first term in the sequence, or it's the y value when x equals 0. So it's the first term when x equals 0. And then b is the common ratio. And the common ratio is what you are multiplying by from one term to the next. Notice I didn't say dividing. So what you are multiplying by. So we have to convert, if it's a division pattern, we have to convert that into multiplication to find the common ratio. So what is being multiplied from one term to the next? All right, then review from back in chapter 3. An arithmetic sequence is a sequence with a pattern involving the same number being added or subtracted. So we have multiplied or divided, that's geometric, added or subtracted, that's arithmetic. And arithmetic sequences are linear, and their general form is f of x equals mx plus b, where b is the first term when x equals 0. And m is the common difference, because that would be like the slope or rate of change. So how much is being added or subtracted from term to term? All right, next slide. It's our then slide. Then we related arithmetic sequences to linear functions. So that was back in chapter 3. And now we're identifying and generating geometric sequences and relating geometric sequences to exponential functions. So arithmetic sequences are linear, geometric sequences are nonlinear. And then the Y says you send a chain email to a friend who forwards the email to 5 more people. And each of these 5 people forward the email to 5 more people. The number of new emails generated forms a geometric sequence. So you send it to 5 people, and each one of them sends it to 5. So that makes it exponential because it's multiplied by 5 each time. All right, now our first set of examples says identify the sequence as arithmetic, geometric, or neither, and explain. So that means that we are trying to see if it's an addition or subtraction pattern, a multiplication or division pattern, or neither, because they don't have to be arithmetic or geometric sequences. So you're just going to have to try to figure out the patterns. For the first one, I can tell that it's divided by 2 each time, so that makes it geometric. So you might just need to use a calculator and try it out. The next one, though, it's going up 5, but then it's going up 3, but then it's going up 6. So that's neither. It's not a multiplication pattern either when it goes up like that. Okay, the next one, From term to term, I can tell it to multiply by 3, so it's geometric. And the next one is going by 5s, and it's going up 5 each time, so that one's arithmetic. And then the last one goes up 6, but then it goes up 8, so that's neither again. Okay. Now we're going to focus on just the geometric ones, find the common ratio and the next 3 terms. So the common ratio is what it's multiplied by. So my first one, to go from one term to the next, is multiplied by -4. When it switches from positive to negative, that's an indicator that it's multiplied or divided by a negative number. So the next 3 terms, if I keep on multiplying by -4, -64 times -4 is 256. Then if I multiply by -4 again, I get -1024. And then finally, 4096. All right, next one has a division pattern. It's divided by 3. If you're dividing something by 3, that is the same as multiplying by the reciprocal. So the common ratio is multiplied by 1/3. So 1/3 times 1/3 would be 1/9. Multiply by 1/3 again, and I get 1/27. And then multiply by 1/3 again, and I get 1/81, 1/81st. Okay, my next one, multiply by -5. So 375 times -5 is -1875. Times -5 again, 9375. And the final time, -46,875. Definitely one calculator for these. All right, the bottom one. Now, this one doesn't look very easy to figure out. So what I'm just going to do is I'm going to take 2 of these terms, and I'm going to divide the second term by the first to figure out what that ratio is. That always works because the inverse of dividing is multiplying. So these are multiplied by 1.5. So you can always do that on any of these problems. Take the first 2 terms and divide the second one by the first to figure out what's being multiplied by. So 81 times 1.5 is 121.5. Multiplied by 1.5 again, 182.25. And then last, 273.375. All right. Now we're writing an equation and function notation for the sequence, and then we're finding a specific term number. So f of x equals a times b to the power of x. First term when x equals 0, and common ratio. So this sequence has a first term of 6, and it's being multiplied by 3 each time. So I'm going to write 6 times 3 to the power of x. All right, now this is our exponential equation that represents this geometric sequence. Now what I want you to think about is how this goes together. So my sequence, take a look at this. When x is 0, 1, 2, my first 3 terms are 6, 18, and 54. So when I plug in 0 for x, anything to the 0 power is 1. So 6 times 1 is 6. It gave me 6. So now what they're asking for is what would be the 10th term. So if I plugged in 10, what would be the y value? Now, what's tricky about this is that 0 gave me the first term in the sequence. So if x equals 0 gives me the first term, and x equals 1 gives me the second term, and x equals 2 gives me the third term. Do you see the difference here? Comparing these values, they don't match. So I can't plug in 10 to get the 10th term. I'm going to have to, if I plug in 0, I get the first term. If I plug in 10, I'm not going to get the 10th term. So because I need the 10th term, I need 10 here. I hope you're following this. I need to plug in 9 because they're one less. X is one less than the term number, or yeah, X is one less than what term you're looking for. So I actually need to plug in 9. So 6 times 3 to the 9th power. So that would be 118,098. So 118,098. If you are in doubt, you could always just continue your sequence. It's just going to take a lot longer, I think, to get to the 10th term. On one where they're looking for something like the 5th term or 6th term, then you might just want to continue your sequence. All right, this next one is multiplied by -4 each time. So f of x equals first term 1 multiplied by -4 each time to the power of x. So there's my equation. So again, think about finding the 15th term. So first term was 1, second term, -4, third term, 16, and this is when x equals 0, x equals 1, x equals 2. So if I need the 15th term, I'm going to have to be one lower, so I have to plug in 14. So 1 times -4 to the 14th power. This is a huge number. So -268,435,456. Now double check this just to make sure. So -4 to the 14th power. So the only thing that's off is it should not be a negative, because if you have a negative to an even power like 14, it would be positive. All right, last example, I think. Nope, 2 left. Okay. So this one, first term, so f of x equals, first term is 120, and this time it looks like a division pattern, dividing by 4. So that's the same as multiplying by the reciprocal, which is 1/4. I'm looking for the 6th term. So if you wanted to continue this pattern, it wouldn't be that bad, but I'm just going to plug in 5. I know that it's 1 less because of x starting at 0. So 120 times 1/4 to the power of 5. So 0.1171875. Very small. And our last example for today, f of x equals, first term -36. And this one is multiplied by, well, it looks like it's divided by -2. So dividing by -2 is multiplying by -1/2. And I'm looking for the 7th term, so I can substitute 6. So -36 times -1/2 to the power of 6. Equals -0.5625. All right, that is it for today. So writing equations for geometric sequences, finding the next 3 terms, or finding a specific term number, and determining if sequences are arithmetic, geometric, or